So now we are ready to introduce our final implementation of this hash map called the separate chaining hash map. As a reminder, where we just left off was we had this simple hash map that used this mod function to wrap the integer keys into a valid index, but we ran into this idea of collisions. And so this separate chaining idea is our approach to resolving those collisions, making sure that those collisions don't cause a problem. Pretty much every implementation of HashMap out there that you'd use in Java or Python use this idea of this separate chaining hash map. Now, before I explain what separate chaining means, I do want to mention if you are looking at stuff elsewhere, like online, and you see people talk about collision resolution or how to handle collisions in hash tables, you'll generally see this one thing called separate chaining, which we will talk about in this class. And sometimes you'll also hear about this other thing called open addressing. Open addressing is fine. There's nothing wrong with it necessarily. It tends to be a little less popular. So we're just not going to talk about it in this class. It could definitely be a bonus topic if you want to go look that up. It's pretty interesting. But for us, we're only going to focus on this separate chaining idea this quarter because it's so much more common. So here's the idea for separate chaining. We ran into a problem with collisions when two different keys mapped the same index, right? We had that key 20 and that key 0. So the idea is instead of just storing one value at each index, let them be roommates. Let's store a data structure there to keep track of all of the keys that map to that index. So we're going to consider each index, we usually will call them buckets. And that bucket is going to be a linked list or something linked lists are a common implementation to form these chains at each bucket location. And what that means is that when you run into a collision, that's not a problem because you could just add another link to that chain. So when item X hashes to index H, so we say, oh, okay, well, this key maps to this index. If the bucket's empty, create a new linked list there and just store that one value in it. Otherwise, just add this value to the list. Now, one thing that we might run into with how I've shown you in this picture is, for example, what should I do if I call get passing in the key 11? Okay, so the way we described this before was you mod by 10, 11, or the size of the array. 11 mod 10 is 1, so we go to index 1 here. Oh, and there's two values here, but I don't know if one of those belonged to the key 11 or which one belonged to the key 11. I don't even know if the key 11 was used here. So we actually can't just store the values here. We need to also make sure to store the keys as well. So in these buckets, you're going to store key value pairs because we need to know whether a particular key, what is associated to this value. Now, how you represent this is actually kind of up to you. There's lots of freedom for how you can represent this key value pair, and you get to choose kind of what you want to do in your implementation on the project. But do remember, you do need to look at when you are trying to search one of these buckets, you have to be checking against the key you're looking for. So remember, the client is thinking about these in terms of keys that vary, that could be really, really large or really, really small. But we are using this hash function to internally turn them into an index. And that index tells us which bucket it belongs into. But you still, since there's going to be collisions, you still need that key there to know, well, does this value belong to the key the client's looking for? That's one thing to keep in mind. Now, what I have here on the page is what we call pseudocode. So pseudocode is supposed to be a formal description of an algorithm, but it doesn't use exact Java syntax. The idea is that this pseudocode is fake in some sense. It's not supposed to be real Java code. It's supposed to describe the idea of the computation without getting bogged down by the details of any particular programming language. So the get method, the way we would implement this now, is you start by computing which bucket the key belongs in. So if they say get for a key, we still use our same trick. We just mod it by the length, and we say, okay, we go to this bucket. Then what we need to do is we need a loop through each key value pair at that bucket. And if we find the key we're looking for, then we can return its value. Otherwise, if we make it through the whole bucket without finding the key we're looking for, we know that the key is not in there because it should have been in that bucket, because that's our mapping from key to bucket, is that hash function. And since it's not there, we can return, hey, there's no such key in our data structure. So that's the idea here. So let's try analyzing the runtime of this structure. Now, the first question is, are there different possible states that this hash map could be in that could yield faster or slower runtimes? So does something other than the number of key value pairs in the whole map affect what our runtime is? And you might already start to see from our description of the pseudocode, the runtime for get really comes from how long the chain in the bucket is, right? If that's really long, we might have to do a lot of looping. We might have our worst case where we're looking at a key at the end of that bucket versus our best case where it's at the beginning. And I kind of already hinted at what's going to go on here. We're going to have to use case analysis because something other than the number of key value pairs in the whole structure is affecting its runtime. The layout of the key value pairs affects the runtime, which means we're going to need cases. So, since the length of these chains determines this runtime, let's try to do some case analysis. So let's start with the worst case. So it's possible that every key value pair that we enter into the system will always hash to the same bucket. So for example, if they always put in a key that when you mod it by 10 is 1, you can end up with this really long chain. And I would argue for that you could come up with a code model using that pseudocode to describe what's the runtime for looking up this key. And I would argue that that takes big theta event time after you do asymptotic analysis on it, because you're going to have to loop through all n elements. So consider, for example, calling get on 51. So you first start by hashing using the hash function to figure out which bucket it belongs to. 51 mod 10, that should say it belongs to index 1, not index 5. I'll fix that afterwards. We start at index 1, and we loop through until we find the key 51. But the key 51 is until the end, so we're going to check all n things. So that's why we are arguing that's going to be big theta event. But notice this is only one case in our case. We can have other cases in our case analysis. Even though in this case we lost our big theta of 1 runtime, we could still consider other cases, right? So consider the best case. So our best case, I would argue, is when all the values are kind of evenly spread out, when not everything is clumped together in the same bucket. And in that case, I would argue that it takes big theta of 1 time. So consider if you're trying to get the value 22, use the hash function mod 10 to get index 2. And then, since in our best case, we're going to say at our best case, every bucket only has 1 element, we just look at that 1 element there and see if it's the key we're looking for. This is just a constant time operation, right? Constant time to get to bucket 2 because we're saying go to array index 2. And since in our best case, there's only going to be 1 element there, all n minus 1 other elements are in other places in the array, then we could say, oh, it's only going to be constant time. So the key to a successful HashMap implementation is to make sure that our buckets are as close to this best case as possible. That's the key here. All implementations of HashMap that get this constant time runtime, they're doing everything in their power behind the scenes to keep the internal representation as close to this best case as possible. So what this ends up looking like is what we're going to call an in-practice case. What I was just saying there was that a well-implemented separate chaining HashMap will stay very, very close to this best case. What we mean by this is most of the time, the operations you're going to be running are fast. It's very rare that you're going to run close to this worst case or run into an expensive operation. And kind of the key to staying close to this best case is making sure you have a good distribution across all the buckets and that the buckets don't get too long. And the one way we can do that is make sure that we're resizing the hash table, making it bigger. What I'm going to argue is that in this in-practice case, which is going to be really close to the best case, we're going to get big theta of 1 runtimes across the board for put, get, and remove. In this table on the right here, I show that the worst case is still valid. You'll still get big theta of n. But in the best case and the in-practice case, which will be close, we'll get this constant runtime. Now, what's going to end up happening is this in-practice case is going to describe what almost always happens in our hash map in practice. The items are going to end up being fairly evenly distributed, and our resizing to make sure that the buckets aren't getting too long, that's not going to happen too often. We're going to assume in our in practice case that's usually not happening. This is similar to something I'm going to just call out real quick called this amortized analysis. We are not going to do that in this class. It's very interesting, but it's a little complex, and we are not going to focus on that. Now, pause for a second. I'm just talking about this in practice case, which sounds kind of loosey-goosey, and you might be blistering a little bit because you might be saying, whoa, wait, Hunter, we just spent 2 weeks doing all this mathematical rigor, and then you're telling me to just throw that all out and just say, well, in practice, it's not going to happen. No, I'm not telling you that. I'm actually telling you to use the framework that we came up with. Remember, in order to do algorithmic analysis, we separated that process into 2 separate steps. Code modeling, which includes case analysis, and then asymptotic analysis on top of that. What I'm arguing here is that this in-practice case is just a different case we can analyze. This in-practice case is basically our best case, but just one that we're going to end up seeing in practice quite frequently. And this in-practice case yields a runtime function that then you could do big theta, big O, big omega analysis on, our asymptotic analysis. So this is actually using our toolbox, but being very explicit and saying, this is a particular case I'm considering here. Now, you may not believe me that this case actually happens in practice, but it is a case that we're going to care about, and in fact does end up happening in practice if we're careful. So that first issue I want to talk about, that resizing. The thing that slows down our implementation, the thing that makes us go from that in practice or best case to that worst case, is if these buckets get too long. If the buckets are too long, then anytime you search a bucket, you have to scan through all the key value pairs there. And so if these things get too crowded, then our runtime starts approaching this big theta event. So the idea there is if you keep your number of buckets constant, then as you add more and more elements to your hash map, the ratio of the number of elements to the number of buckets, well, that still just approaches theta of n because the number of buckets is constant. We kind of just drop it. So one idea is, well, to resize it so everything has a little bit more room. So when our array starts getting too full, which we'll define what too full means in a second, we can resize. Just make a new array that is twice as big. Now, one thing you have to be very careful about is in your implementation, you can't just double the number of buckets and call it the end of the day. Remember, all of our values were hashed using the original size of the array as our hash function. We modded by the original size. So for example, key 7 went to index 2 because 7 mod 5 is 2. But now if we double our size of our array and someone looks up the key 7, well, we're going to say, okay, 7 mod 10 is 7. Oh, there's nothing there. We're done. But that's problematic because we do have a key 7 in there. So you can't just resize. You also have to redistribute the values. And what I mean by that is first make your array twice as big, and then for every key value pair that was already in there, find its new index using your new hash function with the longer array that you're modding by. So you need to recompute the new positions. Do not forget to redistribute your keys on your project. I forgot to do it when I did this project way back when. You're going to forget to do it. Just write a note, get the tattoo on your arm now. Don't forget to redistribute your keys. Don't actually get a tattoo for this class. I don't want you to show that much commitment. But write it down in your notes. Like, I am going to make this bug on this assignment. Let's remember not to do that. You need to make sure whenever you resize that you redistribute all the keys to go to their new valid indices. So be very, very careful about that. The question then is, when should you resize? So I know how to resize. I make this thing twice as long, and then I rehash. I put all the key value pairs in their new indices. Then the question is, when do you resize? Well, in array list, when we use that array backing our structure, we were forced to resize whenever we ran out of room, meaning if our array ever became completely full. Well, technically in the separate chaining hash map, we're never forced to resize because we could just make these buckets as long as we want. But we want to make sure those buckets don't get too long to make sure our runtime is good. And so we need some way of quantifying too full. And so one heuristic we're going to use is we're going to look at this thing called the load factor. Basically what this is trying to compute is the average bucket size. So just take the number of elements, which we call n here, and divide by the number of buckets, we call c. This tells you the average bucket size. And if that value starts getting too large, we know that things are probably getting too crowded. And so we're going to want to resize everything. So here's an example I have this little hash map that's looking pretty darn crowded right now. It has 8 elements and 5 buckets, so its load factor is 1.6, 8 divided by 5. So our rule for resizing is when lambda, we use the Greek symbol lambda to talk about the load factor. I think it's because they both start with the letter L. When this hits some constant value, like the number 1, this is a design decision you can make. What constant do you want to resize at? But once it hits some value like 1, that means we need to, we expect to see 1 element per bucket, or close to 1 element. So we'll have that constant runtime. But if that lambda starts getting really, really large, then we're going to start getting closer to that O event runtime. So the idea is when you hit this value 1, this critical factor, then resize the whole thing and start over again. Now that load factor will be lower. We're going to tell you to double the size of the array. So double the capacity of that array, and it'll turn out if you do that, you follow that instruction to double the size of the array, it turns out that expensive resize operation won't happen very frequently. It happens increasingly less frequently because doubling and doubling and doubling makes this thing bigger and bigger and bigger. But you're only making it bigger so when it starts getting too crowded. And so in that case, even though you're resizing and some operations are slow, it's still in the long run actually going to be very fast for most of the operations you do. Okay? So that's a bit tricky. You resize, and remember, you got to rehash everything, got to redistribute all those values. And when you resize, it's when this load factor, this average values per bucket, gets too large. Okay? That's resizing. The last thing we want to tackle is how do we handle non-integer indices or keys? How can we extend our map to work for strings, for example? So remember, our definition of hash function didn't actually say that the input had to be integers. We can say it's really just any function that can be used to map a data of arbitrary sized to fixed sized values. So a hash function is going to be any function that can turn something like strings into numbers or indices for our array. And so we want our hash function to follow 3 properties. We want it to be deterministic. What I mean by that is that if you give the same input twice, it should always generate the same output. So you don't want it to actually be a random number generator. That could turn any string into a number, but it won't necessarily be a consistent number. We want to be efficient. We want this hash function to be a reasonable runtime so our whole pipeline can be constant time. And we want this hash function to be uniform. We want its outputs to be kind of spread out evenly across the range of all possible outputs. So one valid hash function for the strings is every hash function gets mapped to the index 0. That's valid. It turns any string into a number. But that's not a very good hash function because they're all concentrated at one spot. We really want this uniformity. So I'm going to kind of quickly go through some different hash functions for strings. The important thing here is to not, we want to show you that there are possibilities and there's actually kind of an art to designing this, but we don't end up worrying about these too much in practice because we use the pre-written ones for us. So here's a very simple hash function. If you can take any string and return its length. That takes any string value, which could be really long. I almost knocked over my water bottle. It could be really long and turns it into just a simple number. Super, super fast, but this causes lots of collisions. There are lots of strings of length 4 out there. So lots of collisions will happen here. One idea is you can use this very clever trick that strings are made up of characters, and characters in computers all have numeric values. So for example, the letter A is represented by the number 97, B, 98, etc. And so one idea is to just add up all of those numbers from the characters and return that as your hash function value. This is still pretty fast and has fewer collisions, but it's relatively easy for you to come up with cases that collide. So for example, 2 words that collide in this are dog. Let's see if I can try spelling with my finger. Dog and God. The reason is this hash code, this hash function, doesn't care about order. It just adds them all up blindly. And so it allows permutations of a word, words that have the same letters but in different orders, they're all just going to hash to the same thing. So it'd be relatively easy for someone to come up with collisions. So what we're going to want to do, or what we're going to rely on, is a third hash function, Java's hash function. which does something very similar to implementation 2, but it does something really wacky where it multiplies each character, the integer version of that character, and they multiply it by some number, some prime number in particular. There is no reason why we need to understand how they chose this, how they get those prime numbers, but the idea is to take each character, each index, and multiply it by a different number, and then when you add those all up, we no longer have that permutation problem. So it does some really complex math to combine them, but the pro of this is it has a lot fewer collisions, but it is a little bit slower, and it ends up with really large numbers. Now, why did I rush all the way through all of this? Well, it's because from our perspective of writing the data structure, we don't usually care that much about how they implement their hash function. Hash code, it turns out, is the way that Java objects can determine what their hash function is. So, let's hide this. Don't worry, though, about how do we come up with good hash functions. Experts made most of those design decisions for us. All objects in Java have this hash code method, and that method does some magic to make a good hash function for any of the built-in objects, like string or any of these other ones. You can just assume that the functions or the objects that we use, like the built-in ones, have good hash functions. You call that hash code method, and it returns a uniform, consistent number. There won't be a lot of collisions. Now, one downside, though, of the hash function is because it gives you an int representation, and this int can be really, really large, we kind of need a two-step process. We need to ask the object to find its hash code, calling its .hashcode function. That's going to return a really large or really small number. And then we need to mod it by our number of buckets so we get to a valid index. So you'll see it's this very common pattern where you ask the object to hash itself, it's going to turn itself into a number, and then you take that number and do what we did before, where we just modded it by our size. Okay, whirlwind of things to consider for project 2. That's how we handle any type of object. You just use its hash code. Again, separation of concerns here. The object's job is to implement its hash function. You are just a client of it. The one last thing I want to remind us of is this concept of an iterator. So an iterator in Java is a way to define an iteration order over your data structure. So iterator is an interface that dictates how a collection of data should be traversed. You can only move forward in a single pass. So iterators have two methods, hasNext and next. HasNext returns true. If the iteration is not yet over, there's more elements to go over, and next returns the next one. And in Java from 143, you might remember that there are two ways to use an iterator. You can either explicitly use it, where you say call the iterator method, and then you say while it has next, grab its next value. Or you can use the Java enhanced for loop, also called the for each loop, which actually just has that code on the left behind the scenes. It's really nice syntax for just writing that. Both of these ways are valid ways of getting an iterator. And one of your tasks on the assignment is to implement one of these iterators. So you're going to implement a class that implements this interface that has a hasNext and next and lets you traverse the structure. Now, one thing I want to warn you about is this can get a little tricky for your separate chaining hash map. The reason is the data is kind of laid out in a really complex fashion. The way your iterator needs to work is it needs to start kind of at the top. And when you want to find the next element, you need to find the next non-empty bucket. And once you find a non-empty bucket, you need to start going through all of its values. So next would return this, and then next would return this. And then when you call next again, well, you need to go down to the next bucket that's available and go here. So implementing this logic of keeping track of where you are in the chain and knowing once you reach the end of the chain going to the next bucket in your iteration order can be a little tricky. So you want to make sure you are very careful about that. One of our past TAs said you're not just iterating over some linear data structure, you're playing 2D chess here. So please start project 2 early. It's out for over 1.5 weeks, but for good reason, because particularly this part could be a little tricky. So please remember to read the entire tip section of the instructions and to look back at this video in particular, because we describe all these components. How do you resize? How do you do separate chaining? How do you handle keys that aren't integers? And kind of walking through the idea of what your iterator needs to do. So hopefully with this, you have some tools and strategies for how you think about you're going to tackle this problem. And we hope you can enjoy project 2 because it's going to be a lot of fun.